Welcome and thank you for joining me. In this presentation, we will explore how to design and simulate a standalone photovoltaic system using PVsyst. You can see in this picture, PV panels convert sunlight into electricity through the photovoltaic effect. When sunlight hits the semiconductor material in the PV cells, it knocks electrons loose, creating an electric current. PV panels generate DC electricity, as you can see, but it can be converted to AC electricity using inverters. Before entering the software environment, we want to be familiar with some concepts. The design of the systems can be in PVCs can be categorized into major groups: the standalone systems and the grid-connected systems. And standalone PV systems, they are designed to operate independent of the electric utility grid and are generally designed and sized to supply certain DC or AC electrical loads. In many standalone PV systems, batteries are used for energy storage, and they design based on user needs such as battery storage and load profiles. Another group is grid-connected systems. They connected to the electrical grid, including self-consumption and grid storage options. A grid-connected system is a type of electrical power generation setup that is interconnected with the local electricity grid. As you can see, it can transfer electricity to utility grid. In addition, you can design pumping systems via PVsyst software. Solar power water pumps can deliver drinking water as well as water for livestock or irrigation purposes. As you can see, you should calculate the required PV array size and pump power based on water needs and pumping depths. After you choose the system that you want to simulate in PVsyst, for instance, is standalone or grid connected or solar pumping, you should enter your input data to the software, and after that the software has the ability for hourly simulation and shading analysis. It can evaluate the impact of shading from nearby objects and structures. In addition, it can have the ability for loss analysis. It can identify and quantify different types of losses such as thermal, wiring, and soiling losses. The software has the ability for economic evaluation too. It can provide detailed economic evaluations, including cost of components, NPV, net present value, levelized cost of energy. You should input your data and it can evaluate economically your problem. And it can be used as educational tools. More importantly, you can input methodological data to that through its database that you can see in the software environment as follows. You can install the software through its website, as you can see. And now we want to design standalone solar systems in PVsyst. Therefore, we have this flowchart. First of all, we select our system. It is a standalone in this presentation. After that, we enter weather data, and then you should enter main parameters. There are two kinds of parameters: main parameters and optional parameters. Optional parameters aren't mandatory to define for the software. You can have your simulation if you don't define that. But main parameters, you have to input all of them truly to have the simulation. It includes orientation, users' needs, and after that choose the system, PV array, storage, backup, and finally the detailed losses should be entered to have the simulation. You open the software. After that, choose grid connected standalone pumping. You choose it standalone system, and here we can create a name for that project, create a new project. We can click on that, and we can name, for instance, a standalone system or other thing for your project. You can set a name, and after that you should input weather data file here. So for weather data, we should click on that geographical sites. You can choose it here. For instance, I want to have a simulation for Tehran. So it's a city in Iran, in Asia. So I choose that. You can see the latitude, longitude, altitude, time zone here. And you can see the monthly weather data in each month, the global horizontal radiation, horizontal diffuse radiation, the temperature, wind velocity, and relative humidity, and other parameters here. You can choose the units for irradiation, which is it watt per square meter. And there is the interactive map here. You can choose other places if you want. Here by type the name, you can search and select it here. And the weather data import can be from these platforms, and we choose Meteor, this one, for that. And after choose that, we can import it here. Okay. Back to choose that one. And back to project environment. You can see here now this save icon is activated here after you choose weather data. So you can choose your file and save it. In the PowerPoint presentation, we talked about main parameters and optional parameters for simulation. So here we have to input them to have the simulation. First, orientation. In the orientation section, you should input the tilt of the plane of the PV panel, which tilt angle it should be placed. So here you can choose if the PV panel track the sun and it has a tracker, you should choose here tracking horizontal axis, vertical axis, or other parameters that you can see here, but I choose the fixed tilted plane, and I want to have the simulation for annual, not just summer or winter, so choose that one. And you can see the loss according to this tilt angle is minus 2.5%. and we should choose the angle, the tilt angle here. According to that, it should be, it's better to be 0. So I choose that one, and it is not 0, so this one, yes, it's 0. The uh, latitude angle of the plane of Tehran. First, we choose it for simulation, and we enter the weather data of Tehran. It was a 35, and so it's between -5 to +5 of 35. It could be okay. So you can choose here to have 0 loss. So 33 is okay in this problem. And as Tehran is located in the north hemisphere of the S, so the azimuth angle of the PV panel is 0, as you can see. And okay, we can save. And after that, we should enter users' needs. For instance, how many lamps, television, fridge, dishwasher, um, uh, or other appliances used in the building should be entered here, the power of them, their daily use, and their hourly distribution. All of them should be entered before the simulation. I put data here, 6 LED lamps, for instance, one television, one fridge, dishwasher, domestic appliances, the power of them, daily use of them. I choose here. And for hourly distribution, for lamps, I choose it 7 hours in a day. So in hourly distribution for lamps, I should enter that. For instance, in 6 o'clock in the afternoon to 12, and 6 to 7 in the morning, 7 hours, as you can see. If you want to deselect something, you choose right click. You click on right click to deselect, and left click for select that. For a TV, it's 4 hours. For instance, and for domestic appliances, for instance, fans, 12 hours. 24 hours for fridge, and for dishwasher it's 2 hours. They are okay. So, okay, and save. Now we go to the next step to define the system for this problem. You can see here first we should enter the autonomy and the PLOL. PLOL is the probability of loss of load, and it is common to be 5%. And for autonomy, it demonstrates using only battery, no solar energy. The duration that you choose, that you use and apply battery, and there is no solar energy. So it could be 1, 2, 3, or other numbers. I choose it 1 for my problem. And the voltage of battery, the typical battery voltages for a standalone system are often set at 24 or 48 voltage based on the system size and power required. For our problem, 24 voltage can be suitable. Which is a smaller system in residential or small commercial applications. So it could be 1 for autonomy and 24 voltage for battery voltage. You can see it is the capacity of the battery that is needed is 371 ampere hours, and the PV power capacity is 2.08 kilowattage, and I want kilowatt, and I want to demonstrate how we can calculate these numbers. As you can see in my Excel file here, we use the 6 LED, one television, fan, washing machine, fridge with different wattage and in different hours, and by plus all of them, the capacity, the total daily consumption is equal to 7.54 kilowatt hour. So by having this number, the ampere hour of battery can be calculated through this formula. As you can see, the ampere hour of battery can be calculated by multiply totally daily consumption, autonomy days, divide in voltage, and DOD. DOD stands for depth of discharge, which is the percentage of the battery's capacity that has been used. For example, if you have a battery with a total capacity of 100 ampere hour and a DOD of 80%, it means you can use 80 ampere hour of the battery's capacity. And by calculating this, we have this number for ampere hour of battery. And for expected PV power, to calculate it, this number, we can use this formula, and by having total daily consumption that is equal to this number and multiply over load factor, it is 1.3, and peak sun hours by considering 4 hours that have enough solar radiation to use the PV panel. So the expected PV power equal to that number, as you can see. So come back to the software environment. We should choose the kind of battery according to these numbers. So you can see we can choose among them. The voltage can be equal to 12 volt, and the ampere hour, it can be different. It depends on the number of batteries we can use. For instance, by choosing this one, we have 415 ampere hours of global capacity that can provide this number, and the kilowatt hour of stored energy is equal to that can provide this number. So it could be okay, and you can choose between lithium ion or lead acid batteries, but lithium ion batteries are expensive, so we choose this one. Okay, and this changed again. I choose that. So the number of batteries is equal to 4, 2 in series and 2 in parallel. So in this section, the operating battery temperature, it could be fixed air condition monthly with specified values or external ambient temperature. We assume that it is in the environment, the PV panels are located in the environment, so we choose this one and go to the next sub-array design. In this section, we should choose the PV module and design that. It could be according to the plant power or available area. It depends on your problem. So in our problem, we choose this one, and the plant power is according to that expected PV power. It's 2450 or 2.5 kilowattage. So according to that, we go to this section. Due to some losses in wiring or other parts, we can choose the battery with a bit more wattage. It is a 24 watt voltage, and we can choose the 25, the 25 voltage among these. For instance, I choose that one according to that. So the voltage can be choose according to this, but as I mentioned, due to some losses, we can choose. It's better to choose the PV module with more voltage. Then we go to choose the appropriate controller for the system. A controller regulates the voltage and current coming from solar panels to the batteries and preventing overcharging. It can be direct coupling, MPPT, it means maximum power point, and DC-DC converter. In direct coupling, uh, it connects the solar panels directly to a load or battery without any conversion. There aren't any conversion in this situation. But in MPPT or maximum power point, it adjusts the electrical operating point of the modules to ensure they operate at their maximum power point. And in DC-DC, it is an electronic circuit that converts a source of DC from one voltage level to another. So I choose this one, and in this section, I choose all manufacturers. Among them, the voltage should be equal to that one, and and it can provide the plant power. So I choose. I should select among them 25 volt, 24 voltage, and 2500 wattage. According to that, there aren't any errors here. If there are any errors, you can see in this blue box here. To check the number of modules here, we can go to the Excel file. As you can see, the controller sizing, and after that we have the minimum and maximum voltage of controller. According to that, this the information is here, as you can see. And after we enter these numbers, the minimum number of module is equal to controller minimum voltage to the panel voltage MPP, and open circuit 1 for the next by dividing maximum voltage to the voltage of open circuit, and so it could be equal to between 1 to 4, and I choose this one to that. It could be between 3 and 5, and I choose this one for that. And for backup, in the next step, the backup system, if you want to choose between them, it is used to recharge batteries when solar energy isn't sufficient to meet the user's needs. But I don't want to choose and select something like that generator for this system. So I don't change it, and you can see the simplified sketch of a standalone system that we designed it. It is a circuit, as you can see, and another thing that I want to talk about, if you click on this section, you can see any information that you need. The open circuit voltage that I refer to that in Excel file, the maximum power point, and the other parameters, the sizes and technology for PV module, the size of that, the weight of that, and its diagram, current in terms of voltage, you can see here, and the other you can choose name for that, or you can go to this manufacturer. It was Trina Solar, some information like that. You can have access to that in this section too. Okay, and I saved that, so you can see all of them are green, so there aren't any error here. It is ready for simulation, but we should enter other parameters too and then simulate it. Go to the next step. As you can see, it's ready for simulation. We can run simulation here, but I talk about optional parameters in the PowerPoint presentation. It isn't mandatory, but you can enter to have a accurate, more accurate simulation. In horizon, it demonstrates the height of sun, yeah, and according to the azimuth angle, and you can give these numbers in some websites, suncalc.org or other websites for according to the location that you want to have simulation for that. Here, according to that one, the height of the sun and the azimuth angle or diffuse factor and something like that. And go to the next step near shadings and simulate and analyze your geometry according to shading simulation. Click on that. You can see here construction and perspectives. Here you can create your elements and your PV tables here according to the number of that. And now we draw PV panels. We assume that they are on the roof of a building and there are some trees there. We want to consider the effect of shading of the trees on the power panels which are located on the roof of the building. So, and create elementary shading object. You can see here, this could be a building that we want to uh, place the PV panels on the roof of that. So you can give that width, length, or other parameters like that. For instance, as you can see, and in addition, you can give that color. For instance, this color or other colors that you want. And when you click on that, you can see this, the color of that. And to input other things like trees that I talk about that, you can click on that and you can give height or other parameters here. And you can see this here. You can modify the location of that. You can choose that one. So if you choose this, you can give it location here. The X, Y, and Z. You can give number to that. I draw the building and trees, and now I want to draw the PV panels here. To create PV panels, go to this section and click on that. And you can see here number of modules in length 3 and 1 here, as you can see. And we can close that. We can see this here, so we should give that location. To add another, because there are 4, we can use Control C and Control P and then give it the location. Now you can see the array of modules, buildings, and trees here. We can export, save, and after that close that. And here you can see the number of modules. It's equal to 12. There aren't any errors here. Just press table button. By press that, you can see the height of the sun and the azimuth angle and the percentage of the shading factor. Other parameters here, tilt angle, azimuth angle, and other parameters that we define the software. You can close that. There aren't any errors here, so it's okay. So we have the report here, as you can see. Here it's the name of the project, the location of that, and the Tehran was the geographical site we used. This is the specification of that, latitude, longitude, altitude, and other parameters. In addition, the kind of the system is a standalone system and 12 units, 12 modules we designed for that. And all of things that we define as the input, all data are here. The tilt angle, azimuth angle, and other parameters, the voltage, and the losses that are here. This is the geometry and the user's needs that we define in the software according to hourly distribution. You can, in terms of hour, you can see the fraction of daily energy, and after that you can see here the amount of unused energy, collection loss, or other parameters according to that. In addition, the global horizontal solar radiation, the electricity, the electric load, users needs, other parameters here, and the input and the output that we have according to that, and the losses that we have, the ohmic wiring loss or other parameters, the percentage of all of them here you can see, and useful out system energy according to global incident on the plane of the PV you can see here. In addition, if you want to have an economic evaluation, you can click on that and you can enter the price of PV modules, batteries, other components, installation, insurance, land cost, taxes, loan bank charges, and other parameters here. And you can choose the currency for that, euro or other currencies here. And so you can have economical and input financial parameters, so you can have economic analysis in this software too. I hope this presentation is useful, and thank you for your attention.